Good morning, everyone. Welcome to Software Engineering. I'm Zhang Shuang from Software College, Northeastern University. Today, we are going to learn implementation and integration. Up to now, some software organizations prefer to integrate after implementation. So you may ask whether it is good or not. Let's discuss about it with an example. Let's say we have a product with 30 modules, A, B, C, D, E, F, G, H, I, J, K, L, M. So let's see, to test module A, module B, C, and D must be stubs. Just now we say that module A is supposed to call module B and module C and module D. Well, at this moment, module A is implemented, but module B and C and D are not available. So, to implement and integrate module A, we must make stubs for module B, C, and D respectively. You can make the stub empty module. Okay, that means it do nothing. Or it can print some message. For example, for module B, it can print it some out. That means give a message to indicate that module B has been visited. You can also return some pre-cooked value. For example, you can say return 0, let's say. So this 0 is pre-cooked value. So such kind of module is called stub. Okay. For our example, to test module H, let's say, module H will call nobody, but module E will call H, right? Okay. So to test module H on its own requires a driver. So that means a driver should be achieved to call module H for once or several times or maybe many times, and each time checking value returned. Just now we say that module E will call module H, and then we should achieve a driver. So that means inside module E, it should be something like call H to ensure that module H will be called and will execute, right? Okay. So we find that to test some modules, sometimes we may need stub and sometimes we need driver. Well, some other modules, let's say module D, it's in the middle. So to test the module D will require both driver and for module A and two modules, let's say F and G. So this is the concept for drivers and stubs. So let's suppose the programmers will implement the modules first and then integrate them. So that means code and test each module separately first, and then later link all the 30 modules together and test the product as a whole. So what will happen? Okay. Problem 1. Implement and then integration will cause stubs and drivers must be written and then thrown away after module testing is complete. So that means the stubs and the drivers will be used for only module testing, and then they will be discarded. So that means a waste of work, right? Okay. And the problem 2, it will cause the lack of fault isolation. That means you integrate all the modules together and test them as a whole, and the fault may lie in any of the 13 modules or 13 interfaces. Let's say in a large product with 103 modules and 108 interfaces. So that means there are 211 places where a fault may lie. So that means it will be very, very hard to debug and to test, to integrate. So we find that to implement first and then integration is not a good solution. The solution should be combine implementation and integration methodically. So this is what we are going to learn in this lecture. That means the software should go through the phase of implementation and integration after design phase. That means implementation and integration should go in parallel. Well, how to implement and integrate the target software system? There are several ways. First, top-down. Top-down implementation and integration. That means if module M1 calls module M2, and then module M1 is implemented and integrated before M2. So let's take this example. Okay. Module A will call module B, C, and D. So in this way, module A is proved perfect. That means it has no problem. And then, based on the step of module B, we can give out the exact implementation. And then integrate module B to module A and do the testing. So now if we get some problem, that means the problem should lie in module B or in the interfaces. It should not lie in module A because module A has been proved to be perfect. So for this example, one possible top-down ordering will be module A first, and module B, C, and D. And then after B, C, and D is implemented and integrated and tested, okay, and they have been proved to be fine, try to implement and integrate module E, F, and G, and H, I, J, K, and the last L and M. This is one possible top-down ordering. Another possible top-down ordering will be A and this branch, B, E, and H. And this branch, A, C, D, and F, and I. And after D, we'll go to another branch, G, J, K, and L, and M. So this means to implement and integrate the target software level by level from top to down. This method really has some advantages. Advantage 1, fault isolation. That means previously successful test case fails when new module is added to what has been tested so far. The fault certainly lies within the new module or in the interface. So that means module A is isolated from the fault. Module A has no problem, and the fault can only exist in module B or the interface. So this is called fault isolation. And the advantage 2, steps not wasted. Step expanded into corresponding complete model at appropriate step. So just now, we have found that after module A is implemented and tested, we come to module B. And now we can turn the step of module B into the real module. We can just add the real logic inside. So that means the step is not wasted. And advantage 3, major design flaws show up early. A software system is composed of both logical modules and operational modules. Logic modules include decision-making flow of control. In our example, modules A, B, C, D, G, and J are logic modules. Let's say the higher level modules such as A, B, C, D, G, and J are logic modules. The modules include the decision-making flow. These are the main design. Well, the operational modules perform actual operation of module. In this example, module E, F, H, I, L, M, and K are operational modules. Okay. With top-down implementation and integration, logical modules, because they are at the higher level, so that's why major design flaws show up early. So that means once some major design flaws show up, the developers can change the design immediately to avoid more waste of time. Well, it also has some problems. Reusable modules are not properly tested. Usually, the operational modules are the most likely reusable modules, but they are at the lower level, so they are not tested frequently. And the situation is aggravated if the product is well designed. For example, someone designed the system in this way. If x is greater than or equal to 0, y is equal to compute square root x. So surely these designers is trying to avoid mistake by making sure that x is valid. Well, maybe it is a good design, but we find that module compute square root will never get a chance to run with a value of invalid. So that means this module compute square root will never be tested with x less than 0. So this module compute square root will not be tested thoroughly, and it will be very hard to reuse it because we don't know whether it is reliable or not. So such kind of programming is called defensive programming. It's also called fault shielding. So this is the problem of top-down implementation and integration. Next, bottom-up implementation and integration. Bottom-up means if module M1 calls M2, and then M2 is implemented and integrated before M1. It will be something like this. Let's say module E call module H, and then module H is implemented and tested first. And then after module H is proved to be fine, try to implement and integrate module E. So one possible bottom-up ordering will be, still this case, L, M, H, I, J, K, E, F, G, B, C, D, and A. Another possible bottom-up ordering is branch by branch. Let's say H, E, B, I, F, C, D, and L, M, J, K, G, and then D. So now B, C, and D are ready, and then module A at last. So it is called bottom-up implementation and integration. Surely it has some advantages. Advantage 1. Operational modules will be thoroughly tested. Because the modules at the lower level are implemented and tested first, they will get a thorough testing, and the operational module will be very reliable, and it will be very reusable in the future. Advantage 2, operational modules are tested with Java, not by fault shielding, not by defectively programmed code modules. So advantage 3 is fault isolation. Module H is implemented and tested first, and once it's okay, we believe that module H is perfect. And then try to implement and integrate module E. So now if we get any problem, the problem will lay only in the module E or in the interface. So module H is fault isolated. Well, bottom up really has some problem. Major design faults are detected late because the modules are implemented and integrated from bottom to up. Well, the major design fault, that means the problem with the logic modules are at the top level, but they are detected late. So once some major design faults are detected, many work has been done for the operational modules. So if the major design has been changed, the work on the operational modules may be wasted. So that's the big problem with bottom-up implementation and integration. So far, we find that both top-down and bottom-up strategies have its own strengths and weaknesses. So the solution is try to combine top-down and bottom-up strategy, making use of their strengths and minimizing their weaknesses. So we get another solution: sandwich implementation and integration. Just now, we found that logic modules is suitable for implemented and integrated top-down. Operation modules will be better if they are implemented and integrated bottom-up. So sandwich implementation and integration is just to try to have logic modules are implemented and integrated top-down, and operational modules are implemented and integrated bottom-up. So in this case, module A, B, C, D, G, and J are following top-down, and the modules E, H, F, I, L, M, K will follow bottom-up because they are operational modules. So finally, the interfaces between the two groups will be tested. We find that the dotted line are the interfaces between these two groups of modules. So we call it sandwich implementation and integration. Advantage 1, major design faults are caught early because logic modules will follow the top-down implementation and integration. Advantage 2. Operational modules are thoroughly tested, so they may be reused with confidence. Because operational modules follow bottom-up implementation and integration, so they will be more reliable. Advantage 3. There is fault isolation at all times. Here we got the summary for implementation and integration. From our discussion, we find that implementation and then integration has no strengths at all, but some weaknesses, including no fault isolation and the major design faults show up late. So surely it is not our choice. Well, top-down implementation and integration has its strengths of fault isolation and the major design faults show up early. Well, its weaknesses is that potential reusable modules are not adequately tested. Bottom-up implementation and integration. Its strengths are fault isolation and potential reusable modules are adequately tested, but major design faults show up late. Finally, sandwich implementation and integration. Its strengths include fault isolation and major design faults show up early, and potentially reusable modules are adequately tested. Well, it has no weaknesses. So we find that actually sandwich implementation and integration will be a good choice. Okay, so much for implementation and integration. Thank you.